Hello and welcome to our lesson on roots and something called their multiplicities. So we're just going to continue to build on our knowledge of polynomial functions, their factors, and their roots today. Just as a recap, we have lots of different synonyms, lots of different names for roots. Roots, when I say that, I'm talking about the x-intercepts for a function, which could also be seen as the zeros or be called the zeros for that function because they are where the y value or the function value is 0. And then we know if we solve the related equation, the solutions to our equation happen to be the same things that we get for our x-intercepts. So our roots, x-intercepts, zeros, solutions, all sort of used interchangeably. And let's build, okay? So if we're looking at y equals x squared minus 4, we hopefully remember this is a quadratic function, this is a parabola, and it's going to be shifted down 4. So just to get a quick visual of this, oops, let's move that axis. If we were to just sketch this out, 1, 2, 3, 4, our parabola in this case looks something like this, okay? And it's going to end up crossing the x-axis 2 times. So where is it going to cross the x-axis exactly? Maybe you can tell by looking at it, which is awesome. If not, let's just put this in here so you can see it. X squared minus 4, crossing the x-axis, there it is, exactly 2 places, at -2 and at +2. So we have a root at -2, 0, and then we have this root at +2, 0. So we have 2 roots, and those are at -2, 0, and +2, 0. Okay, now if we looked at this x squared minus 4 as its related equation instead of a function, so I put the 0 in there instead of the y in there, and I solved this, I could solve using the square root method. So I would add the 4 to both sides, and that would give me an x squared equal to 4, and then I would take the square root of both sides, and that would tell me that x is equal to plus or minus 2. The exact same things that we got for roots, -2, +2, are the solutions here. So these solutions to our equation are the same things we got for the roots for that function, and that's what we've been discussing, okay? Now, here's where it gets interesting. Let's look at y equals x squared plus 4. Y equals x squared plus 4, again, is our parabola, but now it's shifted up 4. So if our parabola is shifted up 4, 1, 2, 3, 4, and we know it's opening up, then where is it going to cross the x-axis? Well, it's not. So we have no roots here. No roots here. Does that mean that our equation has no solutions? Not necessarily, it just means something different is going to happen with their solutions. Now, I can still solve this related equation using our square root method. If I subtract 4 from both sides, it just means that when I go to take the square root, what kind of number am I taking the square root of? Well, I'm taking the square root of a -4, and so my solutions are going to be plus or minus 2i. Our solutions are imaginary. So what we want to see or say here is that there are no real roots. It's just that the roots are imaginary. There aren't any imaginary places on our x-axis. There are no imaginary numbers on that real number line there that is our x-axis. And so our solutions that are imaginary don't translate into real roots or real x-intercepts. So we have when our solutions are real solutions, those real solutions are real roots. When our solutions are imaginary, we do not see them on the graph as real roots. Okay, so we have a graph that isn't touching the x-axis for those 2 spots. So when we're looking at the degree, this is where this is going to get interesting again. The degree is telling us how many solutions we're going to get. So when I look at the degree of 2 in this equation, I know I'm looking for 2 solutions. Well, when I look at the degree for this function, I should be looking for 2 roots. I just don't see them. So that should tell me, if I don't see them, that those roots had to be imaginary. Okay? So again, we're just going to keep building here. What we want to sort of take from this is that all x-intercepts are solutions. If I get an x-intercept, it's going to be a solution, but not all solutions translate into x-intercepts. So solutions like 2i and negative 2i, those aren't going to be actual places where our graph intercepts the x-axis. Okay? Now remember, the degree of our polynomial is going to tell us the total. It tells us the total number of solutions. If we have a 6th degree polynomial, we should be looking for 6 solutions. But only the real ones are going to show up as x-intercepts on a graph. So only real solutions show up as x-intercepts. So for example, if I had a 6th degree polynomial and it only crossed the x-axis 4 times, if it only crossed the x-axis 4 times, that means that 4 of the roots would be real, and that means the 2 remaining had to be imaginary. Okay? So, any remaining solutions have to be imaginary. And then yesterday, or sorry, well, might not be yesterday for you, but in the previous topic, remember we said that those imaginary solutions had to come in pairs. Okay? Imaginary solutions always come in pairs. So it isn't possible to have one imaginary solution, okay, or one complex solution, or one rational solution. All right, so let's look at some functions here. So in this first example, first box here, there's a 3rd degree polynomial function, which means there should be 3 solutions. Now if we look at the graph, this is the graph for this function already created for you. You're welcome. So this tells me there are 3 total solutions. Okay, so total number of solutions, 3. That's based off the degree. I guess I can use my highlighter. Based on that degree of 3, 3 total. Okay, now if we look at the graph, how many times does the graph cross the x-axis? Only once. It's only crossing the x-axis 1 time right there. So there's only one real root, one real solution. Okay, so if there's supposed to be 3 solutions total, but only one of them appears on the graph, what does that mean about the other 2? It means the other 2 have to be imaginary. So that means the other 2 solutions have to be imaginary solutions. Okay, same concept. Let's look here. This degree of my function tells me there should be 2 total solutions. So I'm supposed to have 2 total solutions. Now if I look at the graph, how many times does the graph cross the x-axis? Once, twice. So the number of real solutions happens to be 2. That means this won't have any imaginary solutions. There were supposed to be 2. 2 showed up on the graph. Boom, we're done. Nothing extra or weird happening here. Okay? Now this last one is one for you to try, just to put that concept together, but I didn't put the graph, so I want to make that graph there. I do know, just by looking at the function, that there should be 4 total solutions. But if I graph this, 4x to the 4th, and minus 3x squared, minus 1, I see this sort of W-shaped graph. So if I'm going to sketch this here, it's crossing at -1 and +1. +1, and then, let's see, down here at -1 as well. And then this is decimal, so this is going like here-ish, whatever. I'm just going to sketch this out. So this graph is doing something like this. Okay, so there's my picture. Again, 4 total solutions. That is based off the degree. So this tells me I should have 4 total solutions. But how many of them do we see on the graph? How many times does this graph cross the x-axis? Well, it crosses twice. So if it's only crossing the x-axis twice, that means there are only 2 real solutions, 2 real roots. So if there are supposed to be 4 total and 2 of them are real, that means the other 2 that are remaining have to be imaginary. Okay? Hopefully you're with me so far. Now, continuing. So the multiplicity of a root is what we're going to be talking about next, and it's basically describing the number of times that root occurs as a solution or as a factor of our equation or our function. So the multiplicity of a root, and I might have mentioned this in the previous topic, again, it's describing the number of times that the root occurs as a solution of the function, or sorry, a factor of the function, or a solution to the equation. The same stuff, right? How many times does that root occur as a factor or a solution, depending on if you're looking at the function or the equation? Okay, so remember in our quadratic module, if we had something like x plus 1 and x plus 1 equal to 0, this is a quadratic, so we're looking for two solutions, right? Two solutions here. Well, x equals negative 1 is the same solution twice, so we didn't list it twice, but we knew that when x equals negative 1 was the only one solution, it was because it was the same solution twice, okay? So this can be called a double root, or we could say that this is a root with a multiplicity of 2 because it happens twice as a solution to the equation, or twice as a factor of our function. Okay, so here is a cubic polynomial function in two equivalent forms, and here's the standard form of f of x. This is our standard form, and then here's the factored form. So it's the same function, I just put it in two forms for you to help you see how the multiplicity of our roots, or our factors there, how it affects the behavior at the root. Okay, the multiplicity affects the behavior of our graph at our root. All right, so looking at this graph, this is the graph of this cubic function. What would you say about it? So if it's a cubic function, there should be 3 total solutions, right? 3 total? Okay. How many do you see on the graph here? Well, this looks like 1. This looks like 2. So 2 real? Is that possible? If there were 3 total and 2 of them real, then the last 1 would be imaginary? Is that possible? Well, no, because the imaginaries have to come in pairs. It isn't possible to have just one imaginary solution, which means all 3 of them are real solutions. Now, this is where the multiplicity is going to be helpful here. So notice the behavior of the graph at these two roots is different. At our first root, this guy over here, the graph goes through the x-axis, where we're negative, and then we hit the x-axis, and then we're positive. So we go through the x-axis at that root. But what's happening at the other root is the graph is positive, right? It's positive, it's above the x-axis. It hits the x-axis, and then it bounces back up, and it's still positive. So instead of going through the x-axis, it like bounces off the x-axis. That bounce behavior happens when our roots have even multiplicities, meaning they happen twice, or they happen 4 times, or they happen 6 times. If our root happens an even number of times in our function, then it's going to bounce off of the x-axis. If our root has an odd multiplicity, meaning it happens once, or it happens 3 times, or 5 times, or 7 times, then it will go through the x-axis. Okay, so let's look at our function again up here, the factored form. By looking at the factored form, I can see here that x equals negative 4 is a solution once. So we could see, or we could say that this solution, or this root, I mean, at negative 4, 0, has a multiplicity of 1. It happens once as a solution, and x plus 4 happens once as a factor. So we would say that negative 4, 0 is a root with a multiplicity of 1. Is a root with a multiplicity, that's a fun word, right? Multiplicity of 1. and we would say that is an odd multiplicity, okay? 1 is an odd number. It happens an odd number of times. Now, the other ones here, this x minus 1, x minus 1, oops, I wanted my pen. X minus 1, x minus 1, that's our root here at 1, 0. X equals 1 is a solution twice, right? We got it twice as a factor, twice as a solution. So is a solution twice. So we would say that our root at 1, 0 is a root with a multiplicity of 2. With a multiplicity of 2. And we would say that is an even multiplicity. So that is an odd multiplicity because 1 is an odd number, and that is an even multiplicity, that is an even number. So it happens an odd number of times or it happens an even number of times. And the even or oddness, if that's a word, of our multiplicity dictates the behavior of the root on the graph. So if your root has let's go with odd first. If your root has an odd multiplicity, then the graph goes through the x-axis. If your root happens an odd number of times as a factor or as a solution, it will go through the x-axis. So what does it look like when it's going through the x-axis? It means that before the root, the graph is positive, after the root it's negative, or vice versa. But your graph changes from positive to negative, okay? You're below the x-axis, you hit the root, then you're above, or you're above, then you hit the root, then you're below, but you go through the x-axis, okay? If your root has an even multiplicity, that means the solution happens an even number of times, or the factor happens an even number of times, then what's going to happen is your graph is going to bounce. It's going to bounce on the x-axis. And what does the bounce look like? The bounce means your graph is positive, hits the x-axis, bounces back up, is still positive. It doesn't change sides. It doesn't go through where your graph was positive and then it passes through, then is negative. So it's positive, hits the x-axis, bounces back up, is still positive. Or if it was below, right, then it would be negative, hit the x-axis, and still be negative. So it could bounce underneath as well, but it's not changing. It's bouncing, okay? So when we look at a graph, like this particular graph, I would be counting, again, if I knew that this was a third degree and there were 3 total, I would be counting this once, and then because there's a bounce here, I would have to be counting this one twice. So all 3 roots are really appearing on this graph. You just have to count the bounce an even number of times. And so again, if I know this is a third degree, I know this is a 1, and I know that this is a 2. Now if this was a 5th degree, it'd be a little trickier because it could be that this is happening once, this is happening twice, and that there would be 2 imaginary. That's just impossible to know, so we'd have to know or have to be given more information, if that makes sense. Okay, so those bounces are telling me to be counting those roots an even number of times. All right, so let's look at a couple more graphs. This graph, for instance, it says use the graph to identify the roots and whether their multiplicities are even or odd. Okay, so let's identify the roots. Here is a root at -9, 0. So we have this root at -9, 0. And what's happening at that root is the graph goes through the x-axis, right? We're going through the x-axis, which means that root is happening an odd number of times. So the multiplicity is odd. We would see x plus 9 as a factor once or 3 times or 5 times, some odd number of times. Okay? We have another root. We have another place where we hit the x-axis. That's right there at 2, 0. So at 2, 0, we've got another root, and what's happening here is our graph is going up, hits the x-axis, comes back down, it's bouncing. That entire graph surrounding that root is negative, it is below the x-axis. So that bounce tells me that root has an even multiplicity, okay? That it happens, that means that x minus 2 is going to happen as a factor 2 times, or 4 times, or 6 times, some even number of times. And then I have a third root here, and that is at 7, 0. And what's happening there is my graph is below the x-axis, hits the root, and then is above, right? It's going through the x-axis. And so that's telling me that that root at 7, 0 has to have an odd multiplicity. Okay, so now it says to write a possible equation. Really, it should have been function. Let's write a possible function here. Although the related equation would have the same thing. Actually, let's leave it equation. Okay, a possible equation that has this happening. So we want an odd number of x minus or x plus 9s. If negative 9 is a root, then x plus 9 is a factor, an odd number of times, so I'm just going to put a 1 there. If 2 is a, if 2 is a root, then x minus 2 is a factor, and it's even, so it has to happen an even number of times. And then lastly, if 7 is a root, then x minus 7 is a factor, and again an odd number of times. So if this is an equation, we'd put an equal 0. If this is a function, we would put an equal y. And I guess I'll just put both. So this would be the equation, and this would be the function format of that. Okay, so there it is. They're both kind of the same thing. It's just equals 0 equals y. I don't know why I did that. I'm just flip-flopping here. I'll do a function on the next one, but there it is. And again, this is just a possibility for an equation that would produce a graph that looks like this. It's not necessarily the equation, and but if we put this in a Desmos, we're going to see something that behaves that way. It might not be the exact same graph. It's just a possibility, although the roots will behave the same way. Okay. Now, I just want to show you what happens, or let's confirm this. Okay. Let's say we had x plus 9 and once, and just because I'm going to be messing with those exponents, I'm going to put the 1 in there, and then we're going to have x minus 2, and we're going to do that twice, and then we're going to go with x minus 7, and we're going to put that in there once. And let's go ahead and call this y equals. Okay, so here's a graph, and let me just like zoom way out on this graph, and does it in fact look like the graph we have? Maybe it's not exact. I'd have to mess with the window, but it does behave the same way. Okay, now what I want to show you is not so much these odds. Like if I change this to a 3, okay, it's still going through, but see what happens when I change that to a 3? So I want you to focus on the x plus 9, right? The root there at negative 9, okay? When this was a 1, the graph went straight through. When I changed it to a 3, it's more like a cubic function, where it's still going through the x-axis, but see how it's flatter there? So I know when I see, we call that an inflection point. When that graph goes through, but it goes through more slowly, that means the degree was probably higher. It's still odd, but probably a higher odd degree. And again, if I make that a 5, it's even flatter, so it's even slower. It still goes through, right? We have graph that is above and then hits the x-axis and then is below, so it's still going through. It's still odd, but it's even flatter. And in fact, the bigger we make that exponent, the slower it is going through the x-axis, okay? So I knew looking at the graph that was on the note sheet there that was going to be a degree of 1 because it went straight through without like taking its time, without flattening out, okay? And the same is going to be true for our evens, okay? So let's look at the even one we had over here Let's look at this root at 2. Okay, so there's our root at 2. That's with a multiplicity of 2. It bounces. And I just want to shrink this up a little bit. Okay, so there's our root at 2. Again, it's bouncing, so I knew it was even. Now, if I make the exponent bigger, but still even, it's still going to bounce, but see what happened? Okay, the bounce was flatter, if you could say it. Like, it takes longer to go up and finally come back down. And if I make it a 4, same behavior, but even flatter. Let's make it bigger. Like, it just takes longer for that behavior to occur. So when I see a nice clean bounce, I'm probably going to be looking at a degree of 2. The longer it takes for that bounce to happen, the flatter that bounce looks, the higher the degree. Again, still even because it bounces, but it's just telling me that multiplicity is a bigger even number, if that makes sense. Okay? All right, so just to add on to that, let's get another one. If I'm looking at this next one, my first root is happening here at -4. And at -4, 0, my graph is doing what? Well, it's above, it's still above. It bounces off the x-axis, so I know its multiplicity is even. And that's a pretty clean bounce. Here's another root at the origin, 0, 0. And again, that's a bounce. My graph is above the x-axis, hits it, is still above. That bounces on the x-axis. So again, my root at 0, 0 is going to have an even multiplicity. And again, that's a pretty clean bounce there. And lastly, we have this root at 5, 0, and that does not bounce. The graph is above the x-axis, hits it, and then is below. That goes through the x-axis, so I know that my root at 5, 0 has an odd multiplicity. Okay, and again, it goes straight through, which means it's probably a multiplicity of 1. If it flattened out there, it'd probably be a 3 or a 5 or something bigger. So let's go with function this time, a possible function. So we're going to say y equals, if -4 is a root, x plus 4 is a factor, and it's even, so let's make it happen an even number of times. If 0 is a root, x minus 0 is a factor, an even number of times. And if 5 is a root, x minus 5 is a factor, an odd number of times. Now you may be like, what the heck? Why do I have this minus 0 in there? Just so you could see it. But do you really need a minus 0 in there with the x? No. So, or we could say y equals, I'm going to just go ahead and put that x squared out in front, and then x plus 4 squared, and then x minus 5 to the first. Okay, you could put the minus 0 if you want. It's just not necessary. We don't need the 0 in there. Okay, so there it is. So now you have all kinds of information about division and factors and roots and their multiplicities. So enough for you to work on your practice, but as always, if you need some extra help, just reach out. All right, guys, take care.